Good morning, here we are once again. It's the physics video lecture, Physics 2A video lecture 9. So we're talking about what? Projectile motion. And I'm going to run through the entire project again. And this time everything will become completely clear. We'll begin with a homework problem of the horizontal throw type, which was that bomb being dropped. Okay, so we'll review with a homework problem, and this was chapter 3, problem 28. Okay, so what do we have here? We have an airplane about to drop a bomb. And the question was, how far is this bomb going to travel? It's discussed last time, it's actually going to track the airplane, but let's just say that at time t equals 0, the airplane's at a height h. Actually, that's 0. Let's put the h up here. So here's the ground level. And we'll run this axis right through the airplane, and then we've got our h right there. Okay, and it's going to land here at a distance d. Okay, so the horizontal throw, remember I said this is the one that always goes on the exams, and you want to know this one. And what we have is the following. We have from Kinematics, x equals v0xt, and y equals h minus 1/2 gt squared. So make sure you know where these equations come from. I may put the whole chart up there in a moment. Okay, this is the free fall. It doesn't depend on x, and this is the horizontal motion. It doesn't depend on y. So to solve this problem, and they gave us some speeds. You have to note that of some numbers, the height was in kilometers, so you have to take thousands of meters, and the horizontal motion was in meters per second. We got 275 meters per second, 3 kilometers. Okay, so we had h is 3,000 meters, v0x was 275 meters per second. Okay, I'm not going to plug these in, but those are the numbers you were given. So it's from the second equation. I'll number these. It's from the second equation when y is equal to 0. Here, let's put a y up here for y-axis. When y is equal to 0, what is the time? So that's the time it took to fall. And we solve equation 2, and we find that t is equal to 2h over g, and then we take the square root. So you plug your numbers in, and then you get the amount of time it took for the thing to fall. And during that time, it was moving forward. Okay. So you use this one right here. Equation 1 tells us that the distance traveled is v0x times t, where this is v0x, and this is t, and we could call this t sub fall, or t sub impact, or t sub something. How about impact? Impact. So you found this number by plugging these values in. You brought it into there, and you get the answer. Yeah, that's not too bad, is it? Just take some practice. So this was the way I like to introduce this is the horizontal throw, but next what we're going to do is the projectile motion. And this time I brought along the little cannon, little projectile launcher here that I'll demonstrate a little bit. Wait, this goes up here. I'm going to start with our sketch and then demonstrate it with that projectile motion. Demonstrate it with my device right there. Good. Here's what we had. We had an x-axis, a y-axis, an initial angle, and then we know that the thing goes up, goes to the ground again. We had the range r of the projectile. We had a maximum height, y sub max, and there was time involved. It's a problem just like this one, a little bit more involved. So let's begin with demonstrating these things here. In particular, the 0 level corresponds to the height of the top of this cannon. You see, when the ball emerges from here, it's going to be at this height, which is what we're calling 0. The initial angle can be measured with a protractor. For example, right now I'm reading about 52 degrees. And in keeping with my picture there, imagine I put this ruler up here. Let's see. There we go. So that shows the angle. The ball's going to launch here and fall under that. This is that 52-degree angle to the horizontal. Okay. So I can adjust this. There's a built-on protractor, and then I can do some target practice. Okay, so here is a box that is just a little too high, but I'm going to tip it, and then the edge will be at the level of the muzzle of the cannon here. So we'll put the box like so and tip it a bit so this edge is the same height. We want to see if we can get the ball to go in there. Well, it won't go at just any old angle. Let's go ahead and see what this thing will do by setting it to 0 degrees. Actually, this is 90 degrees straight up. So it has two settings. The weak spring just sends it up a couple of feet. There we go. Okay, it comes up like that. Now I've got a second setting, and this is the one I want to use. It goes up pretty high. And I'm not quite sure how much the video is going to show of this, but we're hopeful. And the third one actually hits the ceiling, and you'll hear it hit the ceiling. Okay, so that one's a little too fast. Now I'm going to show us later how we calculate exactly the angle needed to hit a particular target. That was our range formula. For now, I thought I figured this out before class, and I'm going to do a 75-degree angle. And see what happens. Wish me luck. Apparently I wasn't lucky. But that was 65 degrees and not 75. Let's try this again. Okay, 75, not 65. Now this should do a high arc and land in that box. Give it a try. Okay, it's all one take, no edit, so yeah, that's also too many degrees. This thing's pretty sensitive. Let's try this once more. Okay, I'm doing 75 degrees. Clicks. Bingo. Okay, let's do another one just for good measure. So we've got 75 degrees, and we're doing a high arc and landing in the box. Fantastic. Okay. Now, there's a lower angle where we could just be able to sail into the box, and that one can be calculated. I'm just going to tell you now that that angle is 15. And 15 and 75 are complementary angles. They add up to 90. Okay. I better be careful this time. That looks like 15 to me. Okay. 2 clicks. This is a lower arc. It's going to seem to be moving a lot faster. Okay, we'll do it once more for good measure. So I'm going to have to mathematically verify all these things. Missed that one. I pulled back on it. Okay, once more with feeling. This has got to be 15. Two clicks. Get more 15 than that. Okay, good. Okay, that's all our target practice for today. That was projectile motion. And now we have to work out what we just saw. Okay. So we had an initial angle, we had initial speed, which by the way, we can measure, but that takes a little bit of doing. Actually, I need audience help for the measuring the initial speed. Okay. We have an arc here, and we saw that there was a high arc and a flatter arc that actually met the same target. So let's go ahead and set this up and see if we can get all of this taken care of. So we have v sub x equals v0 cos theta, v sub y equals v0 times the sine of theta. That's from the analysis of this triangle right here. Then we have x equals v0 xt, y equals v0y, t minus a half gt squared from our kinematic equations. And we plugged one into the other last time, and we found y is equal to tangent of theta, I'll put parentheses here, x minus g over 2v0 squared cosine squared theta times, I'll put parentheses here as well, times x squared. So that was the formula for the trajectory. These, of course, can be used individually, independently, the way we just did up here, but now we have a formula for the trajectory. And we had obtained the range formula before. Go ahead and send this up. The range R is the distance it travels before it hits the ground again, and it's obtained when y is equal to 0. So I plug a 0 in here and an R in place of the x. But as we did before with the time-dependent problems, we're going to factor out 1 power up there, and we'll obtain the range formula. So next we have y is equal to tan theta. Let's do this. Factor out x tan theta minus g 2v0 squared cosine squared theta. Since we already have a power of x here, power of x there, and when we set this equal to 0, we plug in r and solve for r. So y equals 0, comma, when r, the range, is equal to 2v0 squared cosine squared theta. I'm just cross multiplying over tan theta over g. Okay, that doesn't look so good, but it's going to simplify a lot. This is sine over cosine squared. And we have sine over cosine. Okay. 2v0 squared over g. Cosine squared theta. Sine theta over cosine theta. There's a cancellation. 2v0 squared over g sine theta cos theta. So that's what we had last time. Okay, we had that formula last time already. I'm going to simplify once more. There's a trig identity. Use sine of a plus b equals sine a cos b plus cos a sine b. That means sine of 2 times theta equals 2 sine theta cos theta. So we're going to replace the 2 sine theta cos theta by the sine of 2 theta. We get a nice formula for the range. R is equal to v0 squared over g sine of 2 theta. Both of these are good, and both of them can be used to understand the complementary angles. This one I'd say is a little simpler to use. First of all, what's the maximum range? The maximum range is very clearly when the sine of 2 theta is equal to 1. So 2 theta is 90 degrees, theta equals 45 degrees. So the maximum range, theta equals 45 degrees. And then we also have these complementary angles that I just demonstrated, namely sine of theta, no, not sine of theta. We're going to have the same range, comma, when theta 1 plus theta 2 is equal to 90 degrees. Those are the complementary angles. So we should write theta 1 and theta 2 have the same range. Here, I'll put that here. Theta 1, comma, theta 2, arrow, same range. When theta 1 plus theta 2 equals 90 degrees. So that's why when I had that thing dialed in to making it into the box at 75 degrees, I knew if I could seek out the 15 degree angle, 75 plus 15 is 90, I'd get the same range. Okay. By the way, if you want to investigate these things, if you have a nice good water pressure and a hose with a nozzle, you can set it up here and then you can see the arc of water. It's parabolic until the air resistance kind of spreads the drops out. But under the right circumstances, you get a very nice parabolic arc. And you can even test out the complementary angles, because there's going to be a low angle where you get the same target as with a higher angle here. So, you know, we can draw it there. You draw it in red. So we have theta 1 plus theta 2 equals 90 degrees, and theta 1 and theta 2 have the same range. Now, I'm just going to have to estimate this one. This looks like it's about 65, so we would be looking at 25 degrees. Okay, 65 and 25 is 90. So we would be looking at something here. You have a flat one and a steeper one. Complementary angles. Okay, let's see how we're doing. Maybe we'll solve another homework problem. Excellent. Okay, so projectiles, where all of this came from, we derived the range formula. This form right here is good. This form here is also good. And you'll notice the range is 0 when theta is 0. That would be a perfectly flat shot that goes nowhere, just rolls. And the range would be 0 when theta is 90 degrees, because 2 times 90 is 180. Sine of 180 degrees is 0. So this formula, you can imagine taking these angles and increasing them. There's a 0 range when you're, there we go, we'll use those. There's a 0 range when you're shooting flat here. As you raise the angle, the range increases. At 45 degrees, it's the maximum range. And think about that when you're trying to throw a baseball as far as you can. And then up at 90 degrees, the range comes back to 0. If this were a hose shooting water, it would go straight up and come straight down at us. Okay, good. So that's our projectile motion. And I think I'll do a couple homework problems that we had. I think this is, let me add one more thing to this. This looks good. There's that derivation. Since the range formula is here, I just want to remind us of the full set of kinematic equations that we were working with this entire time. So, once again, the kinematic equations that we've been working with. People often ask, I don't know, or say, I don't know which equation to use. Okay. You really want to get a chart of the relevant equations. Instead of looking them up in the book, put them down on a page. It's never going to be more than one page, okay? So the kinematic equations, and I'll remind you what we've been doing here. We had x plus v0t plus a half at squared. It's the kinematic equations for constant acceleration. We had v equals v0 plus a times t, and if we didn't need time, we had this third equation. But never forget, this third equation is just obtained from these two, so it's really equations 1 and 2 here. So what did we do? First of all, in the x direction, we let x of 0 be 0, and we said there was no acceleration in the x direction. Okay. So that gave me x equals v0x times t. In the y direction, I changed the name here from x to y, changed the name, and then I also started out at the origin. I had v0 sub y right there, and my acceleration, I plugged in negative g for free fall. Okay, so I still was just using this equation. Good, I caught something up there. You guys can make the correction. Caught my mistake. So watch this. Now for the velocities, I said v sub x was v0x, which was v0 cos theta, and I had no acceleration in the x direction. For the y direction, v sub y, v0 sine theta was v0y, and I forgot to subtract off minus gt. Gotta catch our errors here in real time. Minus g times t. That was v sub y. See, so these two equations, they cover everything in projectile motion. You just have to interpret them for the problem at hand. Okay. Good. Good, so we'll leave this up here now and do another problem. And then I'll assign a couple more as well. Good, so we had some on the homework, a couple more problems I had wanted to talk about. Yeah, 754 and 28A. Yeah, horizontals. Okay, problem 7 in chapter 3 was the complete horizontal throw. It's actually been done completely in the lecture notes, but problem 54 was kind of interesting. So chapter 3, problem 54, this was a waterfall. A landscape architect designs a waterfall, but you saw immediately from the sketch there that it too was a horizontal throw, so we can just label it the way we've been doing here. We've got water coming out at a certain speed from height h. Use another color. We've got v sub 0 in x direction, and this is going to go over to distance d. And they gave us some numbers, so we'll go ahead and remind ourselves what they were. 0.75 meters per second, 2.35 meters. 75 meters per second. And we want to then find out in 2.35 meters. This is just to remind you how big is a person. Well, most people are under 2 meters, so this is just coming over your head right there. But you'll notice this horizontal throw problem is the same as what we've been doing. So we have y equals h minus a half gt squared. So t sub fall, we'll call it this time 2h over g square root. And then d is v0x t sub fall, and then you plug in that number, okay? And then you can judge whether it was far enough for a person to walk under or not. Now the next part of the question was a little tricky. How fast should the water flow in a 1/12 size model? Okay. So what you're looking for is a geometrically similar arc. Okay, you're trying to get a geometrically similar arc, and you have to know the new speed of the water. Okay. So basically, your ratio h to D has to be the same. Okay, so this was no problem here. Now we have, we could call this, we have H sub 1 and D sub 1, and we need H sub 2, D sub 2 to be equal H sub 1 over D sub 1. Okay. We want it to be a geometrically similar to obtain geometrically similar scale model. Scale model. So that's our task. Okay. So what do we have here? H2 over D2 and H1 over D1. So just let's find this H over D. H divided by D is equal to H divided, the other ratio might be better, but since we've started this, let's do this. D is B0x T sub fall, so H over and the time to fall is root 2H over G. So this is the quantity that's supposed to stay the same. So what do we have here? H over the square root of H, we're going to have H to the 1/2 square root of 2. We're going to have square root of G. G doesn't matter, but that's going to stay the same. B0x. Okay. So I'm going to take the square root of G over 2 out here, and then I'm looking at square root of H over B0x. So this is the quantity that has to stay the same. This is how it's going to scale. This is how you scale your speeds and your heights in order to retain the original. Okay, so this is a constant. And once you've determined this constant, then you scale your new quantities according to this side of the equation right here. Because when I said H2 over D2, H1 over D1, that means this ratio has to stay constant. Okay, good. There you have it. So we have one more topic to wrap up this chapter, chapter 3, and that is called, here we go, relative motion. Relative motion. So let's have a look at that. Put a couple problems on board that for a moment. Okay, so new topic. And two good examples for this are an airplane flying in wind or a swimmer swimming against or in a current. So I'm just going to start with those examples, and the formula will come right off of this. So we have a swimmer is trying to cross a stream here. So here's a stream with water flowing to the right at a certain speed. Okay. V of the water, so W. And suppose the swimmer starts at A and wants to make it across to point B directly across, right? It's pretty clear that the swimmer swims forward, the current carries him, forward, current carries him, and actually he's going to end up right here. So in order to make it to B, you'd have to aim upstream somewhere. And the question is, what would your angle be? Well, you'll notice the answer is simply given by vector addition. You're not actually swimming forward and being carried. You're smoothly moving in this direction, but this vector is composed of one that's directly towards B and one that's to the right, if you're just aiming straight up there. So yeah, the formula is simply this. The velocity that he's actually swimming is equal to velocity of the water plus the velocity of the swimmer, if I want to call it that. It's just the vector sum of those. Now, if you want your velocity to be headed directly towards here, you're going to have to head into the stream. But all of these problems are simply vector addition. Vectors add like arrows. You can draw your arrows. In this particular example here, since we have the speed of the stream, you're going to aim in such a direction that these two arrows, right, you're opposing the direction of the speed of the water that way. So this is the direction you would aim, and we could characterize it, say, in this way right there. So for this problem, just draw the vectors and then interpret the different sides of them. And all the problems that we have are going to be of this type. So there was a swimmer, if you had an airplane and this were just the wind that the airplane's flying in, it would be the very same problem. Good. I'm going to assign a couple problems. I'll assign a couple of this type and a couple more projectiles, and then we'll have a good grasp on chapter 3. So let's see, we've got plenty of room here. So this is homework for lecture 9. These will all be from chapter 3. It's always the problems. And I have for you 42, 44, and 52. 42, 44, and 52. We can talk about these next time as well, or actually next week. But what we'll be doing next in lecture 10, force and motion. That will be chapter 4, force and motion. The way it is, we've studied motion pretty thoroughly now, and we're ready to talk about the forces that cause motion. Good, so until next time, have fun with this material.